What if one of the biggest mysteries in modern cosmology is not far away at all, but all around us? What if the Milky Way is drifting inside a vast cosmic void, a region of space so enormous and so strangely empty that it could be distorting how humanity measures the universe itself? If that idea is true, then some of the most important numbers in astronomy may look wrong, not because the universe is broken, but because our location is far more unusual than anyone expected. In this video, we explore the evidence, the science, and the unsettling possibility that Earth may be living inside a giant hole in the cosmos. If this kind of deep space mystery is fascinating, please like, subscribe, and share the channel. Thank you so much for being here and spending time with this journey through the universe. And for those listening tonight, feel free to share what time it is and where in the world this video finds you. Now, let us begin. Space does not first appear to be hollow. It appears crowded, luminous, layered with stars, dust, and the long, faint glow of distant galaxies. Every ordinary image of the cosmos encourages the same impression, that matter fills the universe in every direction, and that emptiness is only the gap between brighter things. Yet the deeper astronomy looks, the stranger that impression becomes. On the largest scales, the universe is not built like a city with objects packed side by side. It is built more like a vast framework surrounding absence. Galaxies gather along filaments, cluster at intersections, and leave behind chambers of astonishing sparseness. Somewhere inside one of those chambers, the Milky Way drifts through its age of observation, measuring everything from within an emptiness so large that the mind resists it. This is the first unsettling fact. The local universe may not be ordinary at all. It may be part of a giant underdense region, a vast cosmological hollow often called the KBC void, named for the astronomers whose work brought it into focus. Its scale is difficult to hold in thought. It stretches across roughly 2 billion light-years. Its matter content appears thinner than expected by about 1/5. It is not an empty hole in the simple sense, because galaxies still exist inside it, including the Milky Way, Andromeda, the local group, and the broader structures beyond them. But compared with what standard cosmology expects at these scales, this whole region seems to contain too little. That shortage may sound modest at first, just a fraction, just a reduced count. Yet once the numbers are spread across a sphere of this size, the shortage stops sounding small. It begins to sound like a distortion in the map of reality itself. The disturbing part is not only that such a region may exist, the disturbing part is that it surrounds the observer. If the local universe is underdense, then light arriving at telescopes does not travel through an average environment. Nearby galaxies do not move through an average environment. Even the effort to decide how fast the universe expands may begin from a location already tilted away from the cosmic mean. In ordinary life, a ruler remains a ruler wherever it is used. A clock remains a clock. In cosmology, the instrument's a stranger. Distances come from exploding stars, from galaxy clustering, from ancient radiation, from subtle shifts in color and brightness. Every one of those methods assumes that the local region is not deceiving the measurement too severely. But if the observer happens to live inside a giant hollow, then the local sky is no longer a neutral platform. It becomes part of the experiment. It becomes one more hidden influence shaping what is seen. The idea does not emerge from fantasy. It grows slowly from sky surveys, galaxy counts, redshift maps, and the long effort to measure the large-scale structure of the universe with greater care than earlier generations could manage. Astronomers in the late 20th century already begin to suspect that matter is not spread smoothly. The first three-dimensional maps reveal walls of galaxies, filaments like stretched threads, and dark regions between them that occupy more room than anyone once imagined. Later, surveys improve the picture. Telescopes on Earth and in orbit count galaxies by the tens of thousands, then the hundreds of thousands, then far more. Instruments supported by NASA, ESA, the Sloan Digital Sky Survey, and many other collaborations refine the cosmic map year after year. As the map deepens, the local region starts to look peculiar. There seem to be fewer galaxies nearby than should exist if the universe around the Milky Way samples an ordinary patch of cosmic space. The deficit does not appear in one direction only, as if some part of the sky were obscured. It appears broadly, in many directions, as though the observer is embedded in a true underdensity. That possibility changes the emotional tone of cosmology in an instant. Before it, the sky is strange but orderly. After it, the sky becomes suspect. One long-held assumption in modern cosmology is that no vantage point is deeply special. Earth is not central. The solar system is not central. The Milky Way is not central. Even the galaxy's location in the wider universe is assumed to be unremarkable once the scale becomes large enough. This principle does not deny local variation. Galaxies cluster. Some regions are richer than others, but it insists that, once enough volume is considered, all places become statistically similar. The KBC void presses against that comfort. If the local region truly spans around 2 billion light-years and still remains significantly underdense, then the scale at which the universe smooths out may be farther away than expected. Worse, the observer may sit in a place rare enough to bias nearly every nearby cosmological measurement. This is where the mystery first deepens. An underdense region does more than contain fewer galaxies. It changes motion. Matter outside the hollow exerts gravitational pull toward the denser surroundings. Galaxies inside the void tend to drift outward relative to the void's center because the stronger mass distribution lies beyond them. The effect is subtle when compared with ordinary intuition, but large when measured across cosmic distances. A void does not push in the way an explosion pushes. Rather, the matter-rich shell surrounding it pulls harder than the matter-poor interior can answer. The result is an outward flow. Galaxies inside such a region can appear to recede faster than expected. Their redshifts can carry the signature not only of cosmic expansion, but of local gravitational imbalance. This opens a troubling possibility. Some of the most important numbers in cosmology may be inflated simply because the Milky Way lives in a hollow region, where galaxies are already being drawn outward more quickly than average. From there, a single question begins to haunt the whole structure of the subject. How much of the universe that astronomy describes is the universe itself, and how much is the view from inside this particular cavity in space? The question does not yet overthrow anything. The oldest light in the cosmos still exists. The large-scale web still forms from early fluctuations amplified by gravity. The standard model of cosmology still explains an extraordinary range of observations. Yet the presence of a giant local underdensity introduces a quiet doubt into every confident statement. It is not enough to ask what the universe does. It becomes necessary to ask where the measuring takes place. The local universe stops being merely the scene of observation and becomes an active participant in the results. There is also a deeper strangeness hidden in the scale itself. Human thought is comfortable with local emptiness. The space between planets is empty enough. The gulf between stars is emptier still. But a hollow spanning billions of light-years belongs to a different order of emptiness. It can contain clusters, groups, wisps of gas, dark matter, flowing galaxies, even a supercluster structure like Laniakea, and still count as sparse. That is the kind of scale involved. Even an enormous population of galaxies can seem like dust inside a region this large. The void does not resemble a clean spherical hole carved through the cosmos. It is more unsettling than that. It resembles a place where structure exists, but not in the expected amount. A place where matter is present, but diluted. A place where the observer can live a complete cosmic life, surrounded by galaxies and still remain deep inside a desert. The name itself sounds gentle, almost technical, almost forgettable. KBC Void, a modest label for a possibility with enormous consequences. If it is real in the stronger sense suggested by some studies, then the local cosmos is not a neutral sample of the universe. It is an exception large enough to lean on measurements, to stir the Hubble tension, to complicate the meaning of homogeneity, and to force astronomy to ask whether the nearest cosmic environment has been quietly misleading it all along. If it is weaker than first claimed, the tension remains. Something still produces the mismatch between what nearby observations say and what the oldest light says. Either way, the same unease remains at the centre of the story. The observer may not be standing on ordinary ground. The cosmos may be measured from within a region whose emptiness bends interpretation before the calculation even begins, and that is where the mystery truly starts, not with a hole in space, but with the possibility that the whole surrounds the act of seeing itself. The first sign of trouble does not arrive as a grand image, it arrives as a count. Cosmology often begins in scenes that seem almost too ordinary for the scale of their consequences. Astronomers gather light, sort distant objects, estimate brightness, compare redshifts, and assemble catalogues one field at a time. The work appears patient rather than dramatic. Yet this is how the deepest cracks usually appear, not through spectacle, but through repetition. A number expected in one bin fails to appear. A pattern that should flatten refuses to flatten. The local universe, when measured carefully enough, begins to look sparse in a way that is difficult to dismiss. In the early years of the 21st century, as galaxy surveys expand in depth and reliability, this suspicion grows sharper. Then a more focused result gives it a name. Ryan Keenan, Amy Barger, and Lennox Cowie examine the distribution of tens of thousands of galaxies across an enormous volume of nearby space. Their analysis, published in the second decade of the century, points towards something deeply uncomfortable. The density of galaxies around the Milky Way appears lower than expected over a huge region, not by a tiny amount that can be shrugged away as the texture of cosmic structure, but by enough to matter, enough to suggest that the nearby universe may sit inside a broad underdensity, extending for roughly 1 billion light-years in radius. The meaning of that result depends on what cosmology expects before the count begins. The standard picture does not claim the universe is smooth at every scale. It expects clumps and gaps. Galaxies gather into groups. Groups build clusters. Clusters line up in filaments and walls. Between them lie voids. All of that is accepted. But the larger the scale becomes, the more those irregularities are supposed to wash out. The average should stabilize. One patch of the universe should resemble another if enough space is included. This is the quiet promise behind large-scale cosmology. A sufficiently large census should stop seeing local quirks and start seeing the cosmic mean. Yet the counts around the Milky Way do not settle down as quickly as expected. Instead, the deficit lingers. Nearby shells of space contain fewer luminous galaxies than more distant shells. The pattern persists across multiple surveys, different parts of the sky, and different methods of estimating the local density. At first glance, it seems possible that something simple has gone wrong. Maybe faint galaxies are missed, maybe dust interferes, maybe one survey selects objects differently from another. But the problem remains stubborn. The more comparisons are made, the less it looks like a bookkeeping error, and the more it looks like a place. That transition is important. A place in cosmology is not just a direction on the sky. It is a three-dimensional region with measurable structure and consequences. To establish such a place, Astronomers need more than images, they need distances. This is where redshift surveys transform the field. The light from galaxies is stretched by cosmic expansion, moving it toward longer, redder wavelengths. By measuring that shift, astronomers estimate how far away the galaxies are, at least in the broad cosmological sense. When those redshifts are combined with sky positions, the flat dome of stars and smudges becomes a volume. Galaxies that once appeared side by side can be separated by enormous depths. Empty-looking regions can prove crowded, and crowded-looking regions can dissolve into unrelated layers. With this third dimension in hand, the universe changes from a painted ceiling into an architecture. It is through this architecture that the local deficit becomes harder to ignore. The missing matter is not confined to one thin patch. It extends outward in many directions. It wraps around the observer with troubling consistency. The studies that support this picture do not claim perfect symmetry. The local universe is messy, threaded with known structures such as the Virgo region, the local sheet, and the broader terrain of Laniakea. But averaged over the enormous scale relevant to the problem, the density still seems low. This is what gives the KBC void its unsettling character. It is not a neat cavity with crisp walls. It is a broad underdensity defined statistically, a region where the average abundance of galaxies falls below expectation, even though islands of matter still float within it. This makes the discovery less visually dramatic than a clean spherical hole, but more physically serious. A cartoon void can be dismissed as an oversimplification. A measured underdensity that survives multiple methods is harder to set aside. It implies that local cosmic geography may be shaping observation in ways that ordinary intuition misses. By this point, the question of probability enters the story. In the standard model, density fluctuations originate in tiny irregularities from the infant universe, amplified by gravity over billions of years. This process naturally produces a web of overdense and underdense regions. Yet the largest and deepest structures should be rare. The KBC void, if its stronger estimates are correct, sits at the edge of what these models comfortably expect. Some analyses suggest that a void of this scale and depth is statistically unusual to a degree that makes cosmologists uneasy. The exact rarity depends on the details of the model and on how the void is defined, but the mood of the issue is clear even without the mathematics. The local deficit looks too large to be completely ordinary. It is not impossible. Cosmology rarely deals in impossibility. But it may be uncommon enough to create a philosophical problem. If the observer lives inside a rare structure, then the assumption of a generic vantage point becomes difficult to maintain. The counting itself gains additional force because it aligns with an older and broader revelation about the universe. By the late 20th century, surveys already reveal great walls, long filaments, and substantial voids. The cosmic web begins to replace older mental pictures of galaxy distribution. The discovery of a large local underdensity does not arrive into a vacuum. It arrives into a universe already known to be more textured than early cosmologists could map. What changes is the scale and intimacy of the anomaly. The web was once something out there, a grand pattern extending beyond the local region. The KBC void brings the pattern home. It suggests that the Milky Way may not merely observe the web, it may reside within one of its largest hollows. This makes the anomaly harder to quarantine as a curiosity. A remote supervoid can remain someone else's problem. A local void enters the calibration of everything nearby. The observational challenge is made worse by the fact that counting galaxies is not as straightforward as it sounds. Bright galaxies are easier to see than faint ones. Different surveys have different magnitude limits, selection rules, and areas of sky coverage. Infrared surveys can reveal objects that optical surveys undercount, especially in dusty regions. Surface brightness effects can hide diffuse galaxies. Distances inferred from redshift can be distorted by local motions as well as cosmic expansion. Every one of these complications offers a possible escape route for anyone who wants the local underdensity to be an illusion. And indeed, some astronomers remain cautious for exactly this reason. They argue that the deficit may be smaller than initially claimed, or less uniform, or insufficient to carry all the explanatory weight later attached to it. This caution matters. The story is strongest when it admits what remains uncertain, but caution cuts both ways. Once many corrections have been attempted and the deficit still refuses to vanish, uncertainty stops being comforting. It becomes part of the mystery. The effect may shift in detail, yet the broad impression stays in place. Nearby space still looks light on galaxies. What gives the count its eerie power is the way it moves from passive observation into active implication. Fewer galaxies nearby means less visible matter, and likely less total matter. Since luminous galaxies trace deeper mass concentrations of ordinary matter and dark matter together, less matter means weaker gravitational deceleration within the region. That in turn means the local expansion can appear faster than it would in an average environment. A local hole in the mass distribution therefore becomes a local distortion in the apparent behavior of the cosmos. Suddenly the galaxy count is no longer just a map, it is a mechanism. It offers a route by which observation itself may be biased. This is where the KBC void stops being a structural oddity and begins to touch the central crisis of present cosmology. Yet before that larger tension fully emerges, the raw emotional shape of the discovery remains worth lingering on. 3 astronomers count galaxies and find the nearby universe oddly thin. Survey after survey helps flesh out the same impression. A missing abundance becomes a surrounding environment. The observer, once assumed to be standing in a statistically ordinary patch of space, begins to look more like a resident of a cosmic outskirts. The old image of the heavens as evenly furnished, once one zooms out far enough, starts to fail at precisely the moment precision grows strongest. The data do not shout, they persist, they accumulate, they deny the comfort of quick dismissal. By degrees, the local cosmos begins to resemble a region where something has drained away, leaving behind enough structure to feel familiar, but too little to feel normal. The most unsettling anomalies are often those that do not erase the known world, but tilt it. The KBC void does not remove galaxies from the sky. It does not place the Milky Way in darkness. It leaves the visible universe largely intact while subtly thinning the population over distances vast enough to matter. That is why the count is so difficult to forget. It does not show an impossible cosmos. It shows a cosmos that looks almost right, then fails on careful inspection. The nearby universe contains galaxies, clusters, filaments, and flowing matter. Yet when the census is compared with expectation, an absence spreads through the numbers like a shadow through water. At that point, the map has already changed. Space is no longer only a stage filled with objects. It has become a landscape in which missing matter carries as much meaning as matter itself. And once that kind of absence is measured, every later mystery inherits it. Once the local deficit begins to look real, the wider architecture of the universe also changes its meaning. A sparse region is not strange only because it surrounds the Milky Way. It is strange because it belongs to a much larger pattern that already pushes against ordinary intuition. On human scales, structure is imagined as something that fills space. Cities spread across land, forests spread across valleys, clouds gather across the sky. Matter is expected to occupy the places available to it, but the universe on its larger scales does the reverse. It does not spread matter evenly through its volume. It pushes most of that matter into a thin, sprawling framework and leaves the greater share of its volume to emptiness. This framework is now called the cosmic web. It is one of the most consequential images modern astronomy has produced, though it is not an image in the simple sense. It is a reconstruction built from millions of distance measurements, redshifts, simulations, and patient comparisons between observation and theory. It reveals a universe where galaxies do not float randomly like grains in still water. They trace filaments, gather into knots, line broad walls, and leave behind bubbles and chambers where almost nothing collects at all. The sheer scale of this arrangement is what makes it so difficult to absorb. A single galaxy already contains hundreds of billions of stars. A cluster can contain hundreds or even thousands of galaxies. A supercluster can spread across hundreds of millions of light years. Yet the web is larger than all of these familiar large things. It is the environment that makes them possible. It is the skeleton on which the observable universe hangs its brightest matter. At the intersections of the web, gravity has done its strongest work. Their galaxies crowd together, gas heats, clusters grow rich, mergers become common. Black holes feed. Between those intersections stretch long filaments, chains and lanes of matter that connect one concentration to another across distances so vast that the brightest cluster can seem like a lantern at the end of a cosmic road. And then, between the filaments and walls, the structure gives way, not completely, never completely, but enough to create regions of such low density that the word void becomes unavoidable. These voids are not rare defects in an otherwise full universe. They are the dominant spatial condition. They occupy most of the cosmic volume. The crowded, luminous regions that astronomy instinctively notices first are the minority. This inversion matters. It means the default state of the large universe is not richness but sparseness, not the bustle of galactic neighborhoods, but enormous underfilled cavities. The web teaches this gradually. Early astronomy cannot see it clearly because the sky offers only 2 dimensions, a dome of points and smudges without depth. A rich field of galaxies may be less a cluster than a chance overlap. A dark patch may hide distant abundance. Only when redshift surveys begin to add depth in a systematic way does the structure snap into focus. In the late 1970s and through the decades that follow, the first major maps reveal the now famous pattern. Galaxies gather along curved and branching features, with large empty spaces in between. Later work by major survey projects turns this into a detailed atlas. The Sloan Digital Sky Survey, among others, helps make the cosmic web visible in a way earlier astronomy could barely imagine. Structures such as the Sloan Great Wall emerge, immense concentrations stretching across scales once thought almost absurd. At the same time, the dark gaps between these giant structures prove no less significant. They are not blank mistakes on the map. They are the map. Once this is understood, the KBC void no longer appears as a lonely aberration. It appears as an extreme member of a known family. That makes it both easier and harder to accept. Easier, because voids are real and expected. Harder, because the size and local importance of this one remain difficult to place inside the normal statistics of the web. The cosmic web already allows the universe to be hollow on tremendous scales. But how hollow, and how close, and how influential can one region become before it starts to strain the model that predicted it? That is the question the local void sharpens. The web gives the concept of cosmic emptiness legitimacy. The KBC void gives it consequence. There is also a physical elegance to how the web forms, and that elegance makes the mystery sharper rather than softer. The standard picture begins in the very early universe, when matter and energy are distributed almost uniformly but not perfectly so. tiny fluctuations, seeded in the first moments and later preserved in the faint temperature ripples of the cosmic microwave background, provide the starting imbalance. Regions that are slightly denser than average attract more matter. Regions slightly thinner lose matter to their denser neighbours. Gravity amplifies the difference. Over immense spans of time, the denser regions become filaments, nodes, walls, and clusters. The thinner regions become voids. In that sense, the cosmic web is what happens when almost nothing uneven at the beginning is given billions of years to grow. It is a spectacular consequence of small asymmetry. Yet this same account also introduces the tension, because if the initial fluctuations are as modest and as statistically well behaved as current observations suggest, then only so much structure should result. Voids of moderate size should be common. Larger ones should be rarer. Extremely large and deep ones should be very rare indeed. The web explains voids, but it does not automatically explain every void that observation appears to uncover. The web also changes the status of emptiness itself. In everyday language, empty means inactive, featureless, almost irrelevant. But a cosmic void is not irrelevant. It is an environment with its own physics. It contains dark matter, though in reduced abundance. It contains thin gas, often mainly hydrogen. It contains dark energy, which appears to be spread through space with a nearly uniform presence, regardless of whether matter is crowded or scarce. It contains galaxies too, though fewer, smaller, and more isolated on average than in denser regions. These interior galaxies do not evolve under the same pressures as galaxies in the busy lanes of the web. They merge less often, they encounter fewer neighbours, they can retain gas for longer, their isolation changes their history. In this way, the web does not merely arrange matter, it creates different kinds of cosmic habitats. A galaxy born in a filament and a galaxy born in a void may inhabit the same universe while living very different large-scale lives. For cosmology, the most unsettling feature of the web is that the voids are not passive gaps. They help govern motion. In a richly populated region, gravity from nearby matter pulls in many directions, often locally balancing in complicated ways. In a void, the imbalance is more coherent. The denser walls and filaments beyond exert the stronger attraction. As matter drains outward and the void expands, the contrast increases. The emptier the region becomes, the less it can resist the influence of the structures around it. In time, the web grows more pronounced. Dense regions become denser relative to the average. Voids become emptier relative to the average. Dark energy, which drives the accelerated expansion of the universe, reinforces this contrast by allowing underdense regions to open more quickly. The cosmic web is therefore not a static pattern frozen in space. It is an evolving tension between concentration and evacuation. The filaments channel matter inward, the voids surrender it. This is why the idea of living inside a large hollow remains so disorienting. The web says that most of space is like this, but the human viewpoint, shaped by stars and galaxies and bright images from telescopes, keeps returning to the minority regions as though they define the whole. Even astronomy is tempted by light. It studies where matter glows, where black holes feed, where supernovae explode, where clusters blaze in X-rays. Yet the larger truth may lie in the silent majority of cosmic volume, in the underdense regions that shape expansion, alter velocities, and place boundaries on what kinds of structures can form. The web quietly announces that the universe is built more from absence than from presence. The KBC void simply pushes that announcement into the local sky. And once the local sky is seen this way, the emotional balance of the cosmos shifts again. The Milky Way no longer appears as a galaxy among countless equals in a generally well-mixed universe. It appears as a galaxy travelling a route through a foam of structure, near enough to a giant hollow that the hollow may enter the measurements made from within it. The local universe becomes not merely a sample of the web, but a privileged and possibly misleading location inside one of its broader chambers. The same structure that gives cosmology its large-scale order also gives it its local uncertainty. The cosmic web is not simply the answer to where galaxies are. It is the reason absence can become a force in the story at all. It makes space into terrain. It makes emptiness measurable. It turns missing matter into a kind of architecture. And once that architecture is accepted, the local void stops looking like an isolated curiosity and starts looking like the most intimate expression of what the universe may truly be, a grand design drawn less by what fills it than by what has fallen away. A void becomes more unsettling when it is no longer imagined as a distant abstraction but as an address. The question is no longer how such hollows exist in general. The question becomes where, within this one, the Milky Way actually sits. The answer is neither perfectly central nor comfortably peripheral. Current reconstructions place the galaxy well inside the broader underdense region, offset from its approximate centre by hundreds of millions of light-years, yet still surrounded on enormous scales by the same lowered matter density that defines the KBC void. That detail matters. If the Milky Way lay close to the edge, the effect on local observations might be weaker, more directional, easier to separate from the background order of the cosmos. But a position well within the underdensity changes the geometry of almost everything that arrives at the telescope. It means that nearby light begins its path in a thin environment, that nearby galaxies move through a thin environment, and that even the transition toward more ordinary density happens only after immense distances. The local universe is not merely adjacent to a void, it appears immersed in one. This immersion feels contradictory because the Milky Way does not seem isolated at first glance. It belongs to the local group, a modest but real gravitational family that includes Andromeda, Triangulum, dozens of dwarf galaxies, and a scattered population of fainter companions. Within this group, gravity still rules in familiar ways. The Milky Way and Andromeda approach each other. Smaller galaxies orbit, distort, and sometimes dissolve into larger neighbours. Dark matter binds the group across distances that would otherwise be impossible for such a loose collection. Nothing about the local group resembles absolute emptiness. It is a functioning gravitational structure with its own history, collisions, tides, and future merger. Yet this is precisely what makes the larger picture so strange. The local group can be real, busy, and dynamically rich while still existing inside a region that is underdense on much larger scales. The contradiction is only apparent. Density in cosmology depends on the scale over which it is averaged. A handful of galaxies can form a close family within a desert that spans billions of light-years. A house can stand in a wilderness. A wilderness remains a wilderness. Beyond the local group lies a wider terrain of cosmic affiliations that makes the same point on ever grander scales. The Milky Way belongs to the local sheet, a flattened arrangement of nearby galaxies moving together through space. Beyond that lies the broader Laniakea region, a vast flow-defined supercluster mapped through the motion of galaxies rather than through brightness alone. Laniakea contains on the order of 100,000 galaxies and stretches across hundreds of millions of light-years. It sounds like the very opposite of emptiness. It sounds like abundance elevated to an almost absurd degree. Yet even Laniakea can fit inside the broader KBC void and still leave that void underdense overall. The scale difference is that severe. A supercluster can inhabit the cavity without filling it. The observer's cosmic home can include enormous concentrations of matter and still remain, on average, part of a hollow. This is where the texture of the void becomes more important than the simple word used to describe it. The KBC void is not a clean bubble with nothing in it. It is a large-scale underabundance threaded with filaments, sheets, groups, clusters, and whatever dark matter scaffolding survives inside it. Its reality, if the stronger version is correct, does not erase structure. It merely reduces how much structure is present compared with what would be expected in an average cosmic region of the same size. That makes the local setting more eerie, not less. The observer does not stand in a pure emptiness that announces itself. The observer stands in a place that looks normal enough to live in, normal enough to build cosmology from, normal enough to mistake for representative. The void hides in averages, not in appearances. It is an anomaly disguised as a neighbourhood. The nearby local void sharpens this feeling further. This smaller but still immense underdense region lies close to the local group and appears to help shape the actual motion of the Milky Way and its neighbours. The galaxy is not stationary against the broader cosmic background. It moves with a peculiar velocity, a motion not caused by the general expansion of space, but by gravitational imbalances in the surrounding large-scale structure. Part of that motion seems connected to the nearby deficit of matter in the local void, and the stronger pull of denser regions beyond it. The Milky Way, along with the local sheet, appears to be drifting away from this underdense zone. This is one of the most important transitions in the whole story. The void stops being something inferred only from counts and becomes something written into motion. It leaves its mark not just on where galaxies are, but on how they travel. That motion is not small in any intuitive sense. Relative to the cosmic microwave background, the Milky Way moves at hundreds of kilometers per second. Several influences combine to produce this attraction toward denser structures such as the Virgo region, the motion of the local sheet, the pull of larger scale concentrations, and the relative weakness of gravity from neighbouring underdense areas. The local void contributes to this imbalance by lacking mass where more mass might otherwise have pulled in the opposite direction. In cosmology, an absence can function like a directional clue. A region with less matter does not shove galaxies away in a literal mechanical sense. Instead, the denser surroundings exert greater pull, so motion acquires an outward component relative to the void. The galaxy's path becomes evidence of a symmetry in the matter, distribution around it. The emptiness is measurable because things are falling away from it. Inside such a landscape, even seeing becomes more difficult to interpret. Every line of sight outward from the Milky Way passes through a region that may be atypical before it reaches more typical cosmic territory. When astronomers examine galaxy counts at greater distances, they often find that density appears to rise toward the scales where the void's influence begins to fade. This creates the impression of a surrounding shell, not necessarily a hard wall, but a transition zone where richer structure becomes more common. If that picture is accurate, then the observer inside the void sees a universe that changes character with distance. Nearby space looks sparse. Farther space looks more crowded. Still farther space approaches the broader average. This naturally affects interpretation. A local survey and a distance survey are not merely sampling different distances. They may be sampling different environments. That complicates every attempt to infer universal properties from nearby evidence alone. The philosophical discomfort grows because the observer's position seems almost tailored to create confusion. Not central enough for perfect symmetry, not peripheral enough for easy correction, surrounded by enough structure to feel ordinary, yet diluted enough to distort averages. A location like this can preserve the illusion of normality while quietly biasing the measurement of cosmic expansion and large-scale motion. It is the sort of setting a theorist would hesitate to assume because it feels too convenient for explaining discrepancies after the fact. Yet the sky does not ask whether a location is aesthetically acceptable. It only presents its distribution of matter and leaves interpretation to follow. If the Milky Way happens to inhabit a broad underdensity with a nearby smaller void, adding local motion on top of it, then the cosmos has built a measuring platform that is useful, detailed, and inherently compromised. What makes this even more intriguing is that the local group itself may owe some of its long stability and character to this broader setting. Galaxies in denser regions experience more frequent close encounters, stronger tidal disturbances, richer cluster environments, and a more violent large-scale context. The Milky Way's neighbourhood is not tranquil in an absolute sense, but compared with the busiest crossroads of the cosmic web, it is relatively calm. The great collisions that dominate the futures of cluster cores are not the daily condition here. The underdense environment may have shaped what kinds of neighbouring structures formed nearby, and what kinds did not. It may have limited the richness of the surrounding region, while still allowing local galaxies to gather into smaller associations. In that sense, the void does not merely distort measurement. It may have shaped the very kind of galactic neighbourhood in which a long observational history becomes possible. Still, this thought opens another uncertainty rather than closing one. If the observer's local environment is so specific, how much of what is learned from nearby structure is general, and how much is provincial? The Milky Way can map its group, its sheet, its supercluster flows, its surrounding voids, and from that build a coherent picture of local cosmic geography. But coherence is not the same as universality. A map made from within a hollow may be accurate locally while still misleading about the wider terrain. This is the quiet tension at the heart of the local cosmic setting. It is rich enough to be studied in detail, structured enough to support sophisticated cosmology, yet strange enough to place every conclusion under a faint but persistent doubt. The observer, then, is not located in darkness or in the centre of a perfect cavity. The observer is located in a layered environment, a galaxy inside a local group, a group inside a sheet inside broader flows, all of it embedded within a region that may be thinner than it should be on the larger scales that nearby surveys can probe. That layered reality gives the KBC void its most unsettling quality. It is not a place apart from the familiar. It is the familiar seen in a larger frame that changes its meaning. The Milky Way remains home. Andromeda remains the future collision partner. Laniakea remains a vast gravitational basin. Yet all of them may inhabit the sparse interior of something larger, quieter, and far less typical than modern cosmology once preferred to imagine. The observer does not stand outside the anomaly examining it from safety. The observer belongs to it. The anomaly becomes harder to contain once it touches the most important number in modern cosmology. A large underdensity around the Milky Way would already be unsettling if it only changed the local map of galaxies. But it does something more serious than that. It reaches into the measurement of cosmic expansion itself. The number at stake is the Hubble constant, the present rate at which space expands on large scales. In principle, that number should not depend on where it is measured. Different methods may be harder or easier, noisier or cleaner, more indirect or more direct. But if the underlying model is right, they should converge on the same physical reality. Instead, they refuse. One set of measurements, built from the infant universe and the fossil light left behind when the cosmos becomes transparent, points toward a slower present expansion. Another set of measurements, built from stars and supernovae in the relatively nearby universe, points toward a faster one. The disagreement is no longer small enough to be a nuisance. It has become one of the defining crises in present cosmology. The reason this matters so deeply is that the Hubble constant is not just another astronomical parameter. It influences the age of the universe, the inferred behaviour of dark energy, the interpretation of structure growth, and the consistency of the entire standard cosmological picture. A shift of a few kilometers per second per megaparsec sounds modest outside the subject, but within it the difference is large enough to signal that something essential may be missing. If the early universe says one thing and the nearby universe says another, then either the measurements are wrong, or the underlying model is incomplete, or the local region is peculiar enough to fool the observer. The KBC void becomes important precisely because it offers a path through that third possibility. It does not require a new force or a new particle at first. It requires only that the measuring place itself be abnormal. The slower value comes from the oldest light that can be observed, the cosmic microwave background, missions supported across decades by NASA and ESA, from the earliest maps through later precision work, reveal tiny temperature ripples in this relic radiation. Those ripples are not random decoration. They encode the conditions of the universe when it is only a few 100,000 years old. By fitting them with the standard cosmological model, astronomers infer the amount of matter, the amount of dark energy, the geometry of space, and the rate of expansion that should follow from those early conditions into the present. The answer that emerges is consistent and remarkably precise. It implies a present expansion rate around the high 60s in kilometers per second per megaparsec. For a long time, this kind of inference is treated as one of the great triumphs of cosmology, because so much else also fits. The primordial light element abundances, the broad structure of the cosmic web, and the age of the universe all sit comfortably within the same framework. The faster value comes from a more local ladder of measurement. It begins with stars whose intrinsic brightness can be inferred from how they vary, then moves outward to Type 1a supernovae, stellar explosions whose luminosity can be standardized with careful observation. By comparing how bright these objects should be with how bright they appear, astronomers estimate their distances. Combine those distances with redshifts and the local expansion rate can be measured directly. This method does not rely on running the entire standard cosmological model from the infant universe to the present. It relies on nearby calibrators, observational care, and the assumption that the sampled region is representative enough for the result to describe the universe at large. Again and again, with refined calibrations and improved instruments, the local value lands higher, around the low 70s in the same units. The tension between the two methods persists through repeated attempts to erase it. If the discrepancy were shrinking with better data, it might simply be the normal pain of precision science. But the opposite has often seemed true. Improvements in calibration, instrumentation, and statistical treatment do not cause the two values to slide peacefully together. They sharpen the conflict. The difference becomes one of the load-bearing anomalies in the field. It is no longer easy to dismiss as sloppiness in the data, and this is the moment when the local void stops being an architectural curiosity and starts to look like a possible explanation of extraordinary reach. A large underdensity naturally causes galaxies within it to participate in an outward flow relative to the denser regions beyond. That flow adds a local velocity field on top of the universal expansion. To an observer inside the underdensity, nearby galaxies can therefore appear to recede faster than they would in a more typical environment. The result is a boosted local Hubble measurement. This is not an arbitrary story pasted onto the data after the fact. It follows from the same large-scale gravitational logic that governs voids everywhere. Where mass is sparse, local deceleration is weaker. Where denser shells surround a hollow, the gravitational pull is directed outward from the hollow's interior toward the richer surroundings. Galaxies inside the void then do not simply ride the global expansion. They move with an additional systematic drift. In many cosmic settings, peculiar velocities cancel statistically when one averages over enough volume. In a large underdensity, they do not cancel so easily because they are not random. They are organized by the geometry of missing matter. The KBC void, if deep and broad enough, would therefore bias the nearby distance ladder upward. The early universe value would remain closer to the global truth, while the local value would become a local exaggeration. That possibility has a peculiar emotional force because it changes the meaning of the disagreement without fully resolving the unease. If the void explains the higher local value, then the standard model may survive largely intact. The Hubble tension would become less a sign of broken cosmology than a sign of an unusual address. Yet this would not feel entirely comforting. It would mean the observer stands in a region special enough to distort one of the central measurements of the age and behavior of the cosmos. It would preserve the model at the cost of weakening the assumption that no vantage point matters very much. In that sense, the void solution is conservative in physics and radical in viewpoint. It saves the framework while compromising the neutrality of the observer. Not all cosmologists accept that this solves the problem. Some argue that the observed underdensity is too shallow, too irregular, or too uncertain to generate the full size of the discrepancy. Others point out that the local distance ladder reaches beyond the most strongly underdense part of nearby space, which should dilute the effect. There are debates over selection effects, calibration subtleties, hidden systematic errors, and the exact profile of the void itself. This uncertainty must remain part of the story. The void explanation is compelling partly because it connects several anomalies at once, but it is not universally accepted because cosmology rarely yields to one clean narrative. The large-scale density field, peculiar velocities, supernova samples, redshift ranges, and distance calibrations all enter the argument. Each refinement clarifies one part while complicating another. Still, the logic of the local underdensity continues to exert pressure because it predicts something specific. If the higher local Hubble value is partly a void effect, then the measured expansion rate should not remain perfectly constant across distance within the affected region. It should tend to decline as measurements extend farther outward, gradually approaching the broader cosmic average beyond the void's influence. This idea sometimes takes on the informal name of a Hubble bubble, a local region where the apparent expansion rate is inflated relative to the universe beyond. That name sounds almost playful, but the implication is severe. It suggests that the most familiar measurements of expansion are made from inside a chamber of systematic bias. Nearby supernovae would not be lying individually. The chamber itself would be bending the meaning of their truth. The consequences spread outward into the age of the universe. A faster expansion rate, if taken as globally true, leads to a younger cosmos. But a much younger cosmos strains against the ages inferred for the oldest stars, globular clusters, and white dwarf cooling histories. The slower early universe value produces a universe old enough to fit more comfortably with those ancient populations. This is one reason the Hubble tension feels so dangerous. It is not merely a mismatch between two techniques. It threatens to loosen the internal coherence of cosmology. The void hypothesis helps because it allows the local value to be high without forcing the whole universe to be young. It says, in effect, that the nearby cosmos is moving through an underdense landscape that makes expansion look faster here than it truly is everywhere. Yet even that rescue comes with an aftertaste of uncertainty. If local structure can tilt something as basic as the Hubble constant, then what else might it be tilting? How many measurements assumed to be universal are really regional? How much of modern cosmology rests on the hope that the local sky is representative, when in fact it may be one of the least representative environments that precision observers could have occupied? The problem is not that the data are false. The problem is that they may be true in a narrower sense than once assumed. They may describe the inside of a large hollow with exquisite accuracy, while only indirectly pointing toward the universe beyond it. This is the quiet horror inside the Hubble tension. The disagreement does not merely threaten a number, it threatens the act of inference itself. A local observer counts galaxies, calibrates supernova, measures redshifts, builds a ladder to the edge of the nearby cosmos, and believes that the result describes space as such. Then the surrounding environment intrudes. The nearby universe may be thinner than average. The local velocity field may be inflated. The expansion may look faster not because the cosmos truly behaves that way everywhere, but because the observer lives inside a place where matter has been drained away on scales too large to ignore. In that case, the universe is not breaking its laws. It is exposing how dependent measurement has always been on location. The KBC void does not need to overturn physics to become profound. It only needs to make the observer realize that even the cleanest number can carry the fingerprint of home. Gravity is usually imagined as the force that drags everything inward. It pulls rain toward the ground, planets toward stars, stars toward galactic centers, galaxies toward clusters. It is the great inward habit of matter. That is why a cosmic void seems, at first, as though it should be irrelevant to motion. If there is less matter in a region, then surely there is less gravity there and therefore less to notice. But this intuition fails on large scales, because gravity does not only depend on what is present, it also depends on what is absent relative to everything around it. In a broad, underdense region, the surrounding walls and filaments hold more mass than the interior. They pull more strongly. The result is not a literal repulsion from emptiness, but a directional imbalance that makes galaxies inside the void drift outward toward the denser surroundings. Gravity does not reverse its nature. It simply reveals that, in a lopsided landscape, attraction from the outside can make the inside behave as though it is being evacuated. This is one of the most unnerving ideas in the whole story. A place with too little matter can still organize motion across hundreds of millions of light years. A hollow in the universe can leave a measurable fingerprint on how entire regions flow. The image that helps most is not a blast wave or a bubble pushing its contents away. It is a basin ringed by higher ground. Matter inside the basin is drawn toward the heavier rims because that is where the greater pull lies. Over immense spans of time, the interior drains. Galaxies move. Dark matter redistributes. Gas thins, and the underdensity deepens. The more matter leaves, the weaker the interior becomes relative to the edges. The geometry then reinforces itself. This is why voids expand faster than the denser parts of the cosmic web. Not because emptiness has become an active pressure in its own right, but because weakly populated regions fail to hold on to matter, while dark energy continues to widen the space between structures. Gravity and expansion combine to sharpen the contrast. Filaments feed themselves. Hollows empty further. The cosmic web grows more extreme with age. For the Milky Way, this is not an abstract principle. The galaxy carries a measurable peculiar velocity, meaning a motion through space that is not simply the general recession created by cosmic expansion, relative to the rest frame marked by the cosmic microwave background. The Milky Way moves at hundreds of kilometers per second. That motion is a sum of several influences, large and small, near and far. The pull of the Virgo region contributes. The broader flows inside Laniakea contribute. The approach toward Andromeda is one local component, but alongside these attractions lies the effect of nearby underdense space. The local void, distinct from but related to the broader KBC environment, helps shape the direction and magnitude of this motion by failing to pull where more ordinary matter would have done so. In practice, that means the Milky Way and its neighbouring galaxies participate in a drift away from the local underdensity and toward richer regions beyond. Even before the broader KBC void is considered, the nearby landscape is already telling the same story. missing matter leaves a directional signature. This has important consequences for how astronomers interpret redshift. In the simplest picture, the redshift of a distant galaxy records the stretching of space between that galaxy and the observer. More expansion means more stretching and therefore a larger redshift. But real galaxies do not merely sit in place while space expands around them. They also move through the cosmic web because gravity pulls them. These extra motions can add to or subtract from the expansion signal. Nearby galaxies are especially vulnerable to this complication because their peculiar velocities make up a larger fraction of the total observed recession. Normally, once observations average over sufficiently large volumes, those extra motions tend to cancel out. Some galaxies move one way, others another. The background expansion emerges cleanly. A large void changes that logic. The motions inside it are not random enough to average away quickly. They're correlated by the same underdensity. Many galaxies share an outward drift relative to the void's interior. This creates a systematic bias rather than a noisy scatter. The result is exactly the sort of broad inflation in apparent recession speed that could imitate a faster local Hubble expansion. This is where bulk flow enters the story. A bulk flow is a coherent motion shared by galaxies across a large region of space. Standard cosmology allows some level of such flow because large structures do create large-scale gravitational gradients. But the amplitude and persistence of observed flows in the local universe have often seemed awkwardly strong. Surveys that estimate galaxy distances through methods independent of redshift, then compare those distances with observed recession speeds, find that large regions move together more than the simplest homogeneous picture would predict. Some of this is expected. Rich structures attract surrounding matter, yet when broad stretches of nearby space show coherent motion at scales of hundreds of millions of light-years, the impression becomes difficult to separate from the influence of a significant underdensity nearby. The KBC void does not stand alone in this argument. It is supported by the fact that the local universe seems dynamically restless in a way that echoes the geometry of missing mass. The beauty and unease of this explanation lie in its economy. No new force is needed at first. No exotic ingredient has to be invented. The same gravity that holds clusters together can evacuate a hollow if the mass distribution is uneven enough. The same cosmic expansion that carries galaxies apart on large scales can become locally amplified in underdense territory. The same web that explains the arrangement of filaments and walls also explains why the spaces between them are not still. Yet this very economy makes the situation more unsettling, because it implies that a crisis in cosmology may arise not from some hidden particle or dramatic new physics, but from something almost embarrassingly simple. The observer may be living in the wrong place to make easy inferences. The cosmos may not be broken. The vantage point may be compromised. There is a second layer to the problem. Peculiar velocity corrections are already a standard part of precision cosmology. Astronomers know the Earth orbits the Sun. The Sun orbits within the Milky Way. The Milky Way moves within the local group. The local group moves within the broader cosmic environment. These motions are not ignored. They are measured and corrected as carefully as possible. But a giant underdensity complicates these corrections because it is not merely one more local motion superimposed on a globally smooth background. It is part of the large-scale background structure itself. The observer is not simply moving through an otherwise average universe. The observer is moving through a section of the universe whose density field already differs from average over extraordinary scales. That means the distinction between local correction and cosmic signal becomes blurred. The void is too large to be treated as a small nuisance, yet too local to be cleanly separated from nearby measurements. It sits exactly in the awkward range where cosmology prefers simplicity and instead finds layered bias. This awkwardness is also what makes the debate so persistent. Some researchers argue that the local bulk flows and peculiar velocities are fully compatible with standard expectations once enough care is applied to the data and the statistical variance of cosmic structure is taken seriously. Others argue that the observed motions are too strong, too coherent, or too suggestively aligned with the local underdensity to dismiss. The details matter. How deep is the void? How sharply does its density change? How far do the coherent flows extend? Are the supernova samples distributed in a way that heightens the effect? Do different distance indicators agree on the same velocity field? None of these questions is trivial, yet beneath them all is a simpler tension. Motion appears to know something about the local absence of matter. The galaxies are not merely arranged around a hollow. They are responding to it. There is something almost backwards about that response. And the backwardsness is what gives the void much of its strange atmosphere. Ordinary intuition expects emptiness to be passive. A lack should have no agency. But large-scale cosmology keeps discovering the opposite. A lack of matter can alter the path of light. A lack of matter can alter galaxy counts. A lack of matter can alter the measured rate of expansion. A lack of matter can even help determine the direction in which great sheets of galaxies drift. The void becomes visible not because it shines, but because the universe bends around its scarcity. In this sense, the hollow is one of the purest gravitational objects in the cosmic web. It reveals structure through what it fails to contain, and once that is accepted, a darker possibility enters. If the local universe is shaped by outward flow from underdense space on scales this large, then many of the neat separations in cosmology may be less stable than they seem. Expansion may be harder to disentangle from environment. Local measurements may carry long memory of the surrounding terrain. The observer may never see a clean universe, only a universe filtered through motion induced by a lopsided cosmic landscape. The Milky Way is not merely sitting inside the KBC void, watching distant galaxies from a still platform. It is being carried through that landscape by gravitational asymmetry, drawn by the richer structures beyond, moving through a vast evacuation that began billions of years ago and has not yet ended. This is why the void feels less like a hole and more like a current. It is not just a region of lower density. It is a direction in the flow of the universe, and anything measured from inside that flow must first answer a hard question: how much of what is seen belongs to the cosmos itself, and how much belongs to the long outward drift of home. The deeper this local hollow reaches into motion and measurement, the more it presses against a principle that modern cosmology treats almost as a form of discipline. The cosmological principle is not a law written into matter the way gravity is written into motion. It is an assumption about the large-scale character of the universe, a claim that once one averages over sufficiently vast distances, no place is especially privileged, and no direction is fundamentally different from any other. Homogeneous means the same in its broad composition from one region to the next. Isotropic means the same in every direction. These ideas do not say that the universe is smooth nearby. They allow galaxies, clusters, walls, and voids. But they insist that all of this irregularity fades into statistical sameness if the view becomes large enough. Without that assumption, cosmology becomes much harder to build. The standard equations that describe an expanding universe rely on the hope that the local wrinkles eventually wash out. The KBC void troubles that hope because it seems to persist across scales large enough that the washing out should already have begun. This is why the void provokes more than observational curiosity. It touches the emotional structure of the subject. For centuries, astronomy has moved in one direction. Earth is not central. The Sun is not central. The Milky Way is not central. Even the galaxy's place in the larger universe is not supposed to be remarkable in any deep sense. Each step strips away another stage on which human observers might claim a special position. The cosmological principle is the broadest expression of that descent from privilege. It says that there is no favoured cosmic address, at least not on the scales that matter most to the universe as a whole. If the Milky Way truly sits inside a giant underdensity large enough to distort fundamental measurements, then that story bends. It does not return the observer to the centre of creation. But it does place the observer in a region whose statistical oddness may matter far more than modern cosmology prefers to admit. The discomfort is not only philosophical, it is mathematical and practical. A homogeneous universe is easier to model because the equations can treat local complexity as noise on top of a smooth background. An inhomogeneous universe forces a harder question. What if the background itself is not so smooth within the range most observations rely on? What if cosmic expansion, local flows, and the growth of structure are being inferred from within a terrain that remains strongly uneven on scales once assumed to be safely average? Then even the act of averaging becomes uncertain. How large must a region be before it counts as representative? How many billions of light years are enough for the universe to stop remembering its local architecture? The KBC void does not merely suggest that one answer may be wrong, it suggests that the threshold itself may be unsettled. Defenders of the standard picture answer carefully here. They note that the cosmological principle has never promised perfection at every finite scale. It is statistical, not absolute. A large void, even a very large one, does not automatically destroy it. The observable universe is vast beyond ordinary comprehension. Rare structures can exist within it without overturning the larger rule. Much depends on how rare the KBC void actually is and how sharply it is defined. If the underdensity is closer to a modest local dip than to an extreme supervoid, then the principle survives with little damage. If the density contrast is nearer the lower end of published estimates, the anomaly becomes easier to absorb into the normal variance of cosmic structure. This is one reason the debate over the void's exact depth matters so much. A shift from 1/5 below average to a smaller deficit may sound incremental, but it transforms the structure from something almost offensively unusual into something awkward but survivable. Yet the principle remains under pressure because the local evidence keeps clustering around the same unease. Galaxy counts look low, bulk flows look stronger than expected, nearby expansion looks too fast. The local environment does not seem to behave like a random patch cut from a perfectly average cosmic fabric. It behaves like a region with character, and character is precisely what the large-scale assumption tries to smooth away. The universe is still isotropic to high precision in the ancient light of the cosmic microwave background, and that observation remains a powerful anchor for the standard model. But isotropy in the ancient sky does not automatically erase the possibility of significant local inhomogeneity in the later universe. One can stand inside a large uneven structure and still see an early universe that appears remarkably uniform when averaged over the whole sky. The tension lies in how the local late-time structure talks back to that deeper uniformity. Some of the resistance to the void interpretation comes from this tension between what is theoretically elegant and what is observationally inconvenient. The standard model works so well in so many contexts that many cosmologists hesitate to let one large local anomaly carry too much weight. The cosmic microwave background, the broad success of gravitational structure formation, the abundances of light elements, and the large-scale distribution of galaxies all fit together with impressive coherence. To abandon the cosmological principle or even weaken it significantly would not be a small correction. It would alter the conceptual frame into which almost all of modern cosmology is poured. That is why the KBC void has such strange power. It is not merely a mismatch in one dataset. It is a local fact, if real, with the potential to make the whole subject slightly less symmetrical, slightly less democratic, and slightly less certain about the innocence of viewpoint. There is another possibility that makes the situation even more subtle. Perhaps the cosmological principle remains true on the grandest scales, but the scale at which it becomes true is larger than many practical observations can easily reach. In that case, the principle survives in theory, while failing in the working range of nearby cosmology. The observer then occupies a universe that is homogeneous eventually but not yet, representative in the abstract but not in the first several billion light-years of measurable space. This would preserve much of the larger framework while still admitting that the local cosmos is a poor guide to the global one. It is a compromise position, and like many compromises, it solves one discomfort by introducing another. A universe that becomes statistically fair only beyond the region most accessible to direct measurement is a universe that makes truth difficult to extract without enormous observational reach. The principle remains intact, but it withdraws beyond the first scales where human observers build confidence. In that setting, the old dream of a cleanly typical observer begins to look less like a fact and more like a convenience. The Milky Way may not be cosmically central, but it may still be cosmically awkward. It may inhabit a zone where the broad rules of the universe are filtered through a local structure large enough to matter and subtle enough to disguise itself as normality. The cosmological principle does not collapse under that possibility, but it loses some of its serenity. It becomes less a statement of obvious cosmic fairness and more a hypothesis under negotiation with data. The universe may still average out in the end, but perhaps not before allowing enormous hollows, strong flows, and biased expansion measurements to accumulate around those who happen to live in the wrong kind of neighborhood. This is what makes the void feel so destabilizing. It does not force an immediate revolution. It asks a quieter question that is harder to dismiss. What if the observer's local world is not special in the old mythic sense, but special enough in the statistical sense to bend interpretation? What if cosmology has inherited from its earliest assumptions the belief that a large enough average is always close at hand, when in fact the nearer scales remain compromised by unusual structure? Then the universe has not restored humanity to any throne. It has done something subtler. It has made the search for a neutral vantage point itself uncertain. The KBC void becomes, in that light, not only a feature of space but a crack in cosmological confidence. It suggests that the most dangerous place in the universe may not be the center of anything. It may be the kind of place that looks ordinary for a very long time, then turns out to have been tilting the measurement all along. If the local hollow seems improbable in the present universe, its roots must lie far deeper than the age of galaxies. A void of this size cannot be created late by chance arrangement alone. It must inherit part of its fate from the beginning, from the faint pattern of unevenness already present when the universe is young enough for matter and radiation to move together in a hot, dense plasma. This takes the story away from the nearby sky and into the oldest light that can still be observed. The cosmic microwave background appears almost perfectly uniform, a bath of radiation cooled over billions of years to only a few degrees above absolute zero, yet it is not perfectly uniform. Tiny differences in temperature are scattered across it, smaller than intuition expects and larger than nothing. Those minute fluctuations are among the most important measurements in modern science, because they preserve the first visible hints of the structure that later becomes galaxies, clusters, walls, and voids. In those weak temperature ripples lies the distant ancestry of every emptiness now stretched across the cosmic web. The standard picture says that the early universe expands through a violent burst of inflation, a phase during which microscopic quantum fluctuations are drawn out to cosmic size. What begins as uncertainty at the smaller scales becomes the template for large-scale reality. Slightly denser regions acquire a head start in gravity. Slightly thinner regions fall behind. The differences are minute at first, no more than 1 part in many tens of thousands, but they are enough. Once the universe cools, atoms form, light decouples from matter, and the radiation that later becomes the microwave background begins travelling freely through space. Matter, however, keeps evolving. It responds to gravity, drains from thinner regions, and gathers into richer ones. Given enough time, the tiny deficits become voids. The extraordinary part is not that voids form, it is that a region as enormous as the KBC void may have begun as a fluctuation so small that it would have been invisible to any ordinary imagination. A subatomic whisper in the first moments of cosmic history may now surround the Milky Way as a desert of diluted matter. This origin story is elegant, but it is not automatically reassuring. The same early universe data that support inflation and structure formation also constrain how wild the later cosmos should become. The microwave background is not a vague hint, it is a precision map. Satellites over successive decades turn the ancient radiation into one of the sharpest pieces of evidence in all of cosmology. First broad maps reveal that the early universe is not perfectly smooth. Later missions measure the ripples with exquisite detail, showing patterns in their angular scales that fit the standard model with remarkable success. These patterns imply a universe whose early irregularities are small, nearly scale invariant, and statistically well behaved. That is why the KBC void remains difficult to absorb. A local underdensity of moderate size is no problem. A giant one that affects key measurements begins to feel like a late-time structure too large for its own ancestry. The early universe seems orderly enough to permit the web, but perhaps not enough to produce a hollow of this scale in the observer's own backyard without a measure of rare luck. This tension is visible in another relic of the early plasma, the pattern known as baryon acoustic oscillations. Before the universe becomes transparent, ordinary matter and radiation are tightly coupled. Pressure waves move through that primordial plasma like sound through a dense medium. When atoms finally form and the radiation is released, those waves freeze their preferred scale into the distribution of matter. Billions of years later, astronomers can still detect that ancient spacing statistically in the clustering of galaxies. It functions as a standard ruler, one of the cleanest geometric tools available for measuring cosmic distance and expansion. This ruler matters to the void story because it provides an independent way to compare nearby structure with the broader universe. If the local region is underdense and dynamically unusual, then the interpretation of this fossil scale in the nearby cosmos can shift in ways that echo the same broader anomaly. The local universe may not only count too few galaxies, it may also place them in a large-scale pattern slightly distorted by the surrounding underdensity and the flows it produces. That is why the earlier sound in the universe becomes part of the modern mystery. The acoustic scale is set in the infancy of the cosmos, long before galaxies exist. Yet it is measured in the later arrangement of galaxies across billions of light-years. If nearby observations of that arrangement disagree subtly with what the early universe predicts, then one of two possibilities grows stronger. Either the universe evolves differently than the standard picture expects, or the local environment is once again bending the interpretation of a deeper truth. The KBC void presses most strongly on the second possibility. It says that the standard ruler remains valid. The early universe remains largely intact, but the measuring location sits in a region whose matter deficit and outward flows complicate the link between local clustering and global expansion. Ancient sound reaches modern space, but it passes through a hollow on the way to inference. The cosmic microwave background contributes something even stranger. It does not only reveal the seeds of voids, it also carries the imprint of later voids along the lines of sight through which its photons travel. As microwave background photons cross evolving under dense regions, They can lose a tiny amount of energy because the gravitational landscape changes while they are in transit. This is one version of the integrated Sachs-Wolf effect, subtle, difficult to isolate, but real in principle and increasingly supported statistically when many voids are stacked together in analysis. Large voids can therefore cool the microwave background slightly along the directions they occupy. The temperature shift is extremely small, but it is measurable in the aggregate. This means that ancient light and late emptiness communicate. A void is not content merely to arise from the primordial pattern. It reaches back and leaves a later signature on the oldest radiation in the universe. This matters because it turns the KBC void from a local inconvenience into part of a longer conversation between epochs. The void may originate in the early fluctuations. It may then evolve through billions of years of gravitational evacuation. Finally, it may influence the light that has crossed the whole observable universe to reach the Milky Way. In principle, the observer sits not only inside a hollow of present-day matter, but also inside a structure whose history connects the earliest measurable conditions to the latest local anomalies. The hollow becomes a corridor linking infant physics to modern uncertainty. It begins as a slight shortage, grows into a cosmic chamber, alters galaxy motion, and perhaps cools the relic light that arrives after a journey of almost the entire age of the cosmos. Some of the most intriguing episodes in microwave background research hint at how powerful voids can be in this context. Cold spots in the ancient radiation have sometimes been linked to supervoids along the line of sight, though such links remain debated and often incomplete. The famous cold spot seen in one direction of the sky is not the KBC void itself, because the KBC structure surrounds the observer rather than appearing as a single distant patch. Yet the broader lesson remains. Large underdensities are not invisible to the microwave background. They can imprint themselves on the most ancient observable light. This strengthens the haunting possibility that local structure may be entangled with cosmic history more deeply than the observer first realizes. It is not simply that present measurements are biased. It is that the same region may connect the statistical pattern of the beginning with the measurement tensions of the present in one continuous chain. There is a peculiar calm to this idea. No violent catastrophe is needed. No cosmic rupture appears. A nearly uniform early universe, a few faint ripples, a long era of gravity, and then, after billions of years, an observer living inside one of the hollows those ripples have grown into. The mystery lies not in spectacle, but in scale. Tiny differences laid down when the universe is young may have matured into a surrounding structure large enough to distort the observer's understanding of expansion, motion, and typicality. The Milky Way may inhabit the grown shadow of an almost invisible early fluctuation. That makes the void feel less like an accident of local geography and more like a deep time inheritance, something written into this region before stars exist, before galaxies turn on, before anything like a habitable world becomes possible, and yet uncertainty remains exactly where it matters most. The microwave background supports the standard model so well that many cosmologists hesitate to blame it for anything beyond ordinary structure formation. The Baryon acoustic ruler is powerful but subtle in local interpretation. The late-time imprints of voids on ancient light are real in concept but delicate in measurement. Nothing here forces a single conclusion. Instead, it creates a widening circle of plausibility. The KBC void may be a natural outgrowth of the very same early universe physics that otherwise works so beautifully, or it may be rare enough to hint that the initial conditions or later gravity have more variance than the standard story comfortably allows. Either way, the emptiness around the Milky Way no longer belongs only to the present. It is tied to the oldest observable patterns in the cosmos. The hollow surrounding home may be a message from the universe's first moments, delivered not as a blaze of revelation, but as a shortage that slowly grows large enough to alter the meaning of everything measured from within it. There is a reason the emptiest regions of the universe begin to matter more, not less, when cosmology reaches its deepest uncertainty. In most places, gravity complicates everything. Galaxies pull on one another, clusters trap hot gas, mergers stir matter into violent rearrangements. Dense environments are rich in information, but they are also crowded with competing influences. A measurement made there has to pass through layer after layer of local disturbance before it can say anything clean about the whole universe. A void is different. A void removes interference. It strips the scene down to expansion, sparse matter, and the persistent background effect of dark energy. That is why the great hollows of the cosmic web have become more than absences on a map. They have become laboratories. They are the places where the universe is least distracted by its own weight. And among those places, a local supervoid becomes especially provocative because it offers not just a remote target for theory, but a lived environment in which the signature of cosmic acceleration may already be shaping every measurement made nearby. Dark energy remains one of the strangest ideas in science because it enters the story through behavior rather than through substance. It is not seen directly. It is inferred from the way space expands. In the late 20th century, observations of distant supernovae begin to suggest that the expansion of the universe is not slowing under gravity as once expected. Instead, it is accelerating. Space does not merely stretch, it stretches ever more effectively over cosmic time. The simplest way to describe this is to say that empty space itself carries a persistent energy density, one that acts like a gentle but relentless pressure built into the fabric of the universe. This idea fits the broader standard model with disturbing success, yet its physical meaning remains obscure. Dark energy accounts for most of the cosmic energy budget while explaining itself almost not at all. It behaves like the most important component of the universe and the least tangible one. In dense regions, the effect of dark energy is partially concealed. Gravity resists it. Galaxy clusters remain bound. Filaments retain structure. Local motions can overwhelm the slow, large-scale tendency of space to accelerate apart. But inside a void, gravity loses much of its leverage. Matter is thin. Clusters do not dominate. Rich supercluster environments are absent or weakened. The same dark energy that exists everywhere therefore becomes easier to notice because there is less ordinary matter to compete with it. A void expands more freely than the denser cosmic web around it. It becomes an open stage on which the universe's large-scale acceleration can perform with fewer interruptions. If one wanted to study the clean behavior of expansion, one would not choose the center of a rich cluster. One would choose an underdense region where gravity has little left to say. This is one reason the KBC void exerts such a peculiar attraction on cosmologists. Even if it proves less extreme than some estimates suggest, it still raises the possibility that the observer already lives in a low-density environment where dark energy's influence is unusually exposed. That would make the local universe both informative and deceptive at the same time. Informative, because it offers a nearby chance to study how expansion behaves where gravity is weakened. Deceptive, because the same setting could inflate measurements and make the local cosmos appear less representative than it truly is. The void would then be a laboratory that contaminates its own experiment. It would reveal dark energy more clearly while also making it harder to infer the universe's average behavior from nearby observations alone. The physics of this becomes clearer when the growth of voids is followed across time. In the early universe, matter dominates structure formation even in regions that are slightly underdense. Gravity still matters there because the entire cosmos is denser than it is now. As the universe expands and the matter content thins out, the relative importance of dark energy rises. In dense regions, the gravitational pull of clustered matter still shapes local evolution strongly. In voids, where matter is sparse to begin with, dark energy begins to dominate sooner and more completely. The hollows widen, their interiors lose matter more effectively, their boundaries sharpen against the surrounding filaments. In this sense, a void is not merely a passive leftover from early fluctuations. It is an evolving structure whose later growth may be driven as much by cosmic acceleration as by its original shortage of matter. The emptiness becomes a place where the future of the universe arrives early. This gives voids unusual diagnostic power. If dark energy is truly constant, then voids of similar size and environment should grow in predictable ways. Their edges should move outward according to a history that simulations can approximate. Their internal flows should follow a characteristic pattern. Their shapes, while never perfectly simple, should remain broadly consistent with isotropic expansion when enough cases are averaged. But if dark energy changes over time, or if it behaves differently in low-density environments, or if some modification of gravity imitates it under certain conditions, then voids may react in ways that reveal the difference sooner than denser structures can. They may grow slightly too fast or too slowly. Their velocity fields may depart from expectation. Their boundary profiles may differ subtly from the simplest model. In that sense, emptiness becomes a test of whatever force truly governs the late universe. This is why large observational programs have turned increasing attention toward the low-density cosmos. The dark energy spectroscopic instrument maps galaxy positions and redshifts with extraordinary breadth, helping trace the shape of the cosmic web and the statistics of voids across vast volumes. The Euclid mission, led by ESA with deep international collaboration, is designed to probe the geometry of the universe, dark energy, and structure growth by observing galaxies over immense distances. The Vera Rubin Observatory is expected to widen the statistical reach even further, recording the dynamic sky while contributing to large-scale structure studies through its enormous survey power. These instruments are not built only to admire the bright universe. They are built to measure what surrounds it, including the underdense regions where cosmic acceleration may write its cleanest signature. As the maps improve, voids become less like curiosities and more like precision tools. Yet the more useful they become, the stranger the local situation appears. A distant void can be treated as an object of study. A local one becomes part of the apparatus. If the Milky Way resides inside a large underdensity, then every attempt to use void behavior to test dark energy must first answer whether the nearby region is typical or exceptional. This creates a mirror effect in cosmology. The void is used to study acceleration, but the same acceleration may help create the very observational bias that forces the void into relevance. The universe becomes self-entangled. The structure used to probe dark energy is itself shaped by dark energy, and may already be distorting the observer's estimates of expansion. One cannot step cleanly outside the experiment, because the experiment begins with the ground beneath the observer's galaxy. There is also a subtler mystery here. Dark energy is usually described as uniform, the same everywhere, because that is the simplest interpretation of current evidence. The large-scale universe behaves broadly as though the energy of empty space does not care whether it sits inside a filament or a void, but the evidence is indirect, and the concept is already difficult enough that even small departures from uniformity would have enormous consequences. Voids, therefore, become places where this assumption can be stressed. If any environment were to reveal a slight difference in the strength or effective behavior of cosmic acceleration, it would likely be where matter is least able to hide the signal. That possibility remains speculative, and must be treated carefully. No decisive observation has shown dark energy to vary from place to place in the strong sense that would overturn the standard picture. But cosmology has learned to respect the places where its dominant assumptions can be tested most severely, and voids are among those places. They are the quietest rooms in a very noisy universe. The KBC void makes that silence intimate. It suggests that the observer may already dwell where cosmic acceleration has a clearer line of influence than in most of the crowded web. If local galaxies seem to stream outward, if the nearby expansion appears boosted, if the underdensity keeps showing up in counts, flows, and local surveys, then dark energy is not merely a distant abstraction acting on remote scales. It is part of the behavior of the region called home. It shapes the growth of the hollow. It amplifies the contrast between sparse interior and richer exterior. It may even be helping to make the local universe progressively less representative as time goes on. The observer may therefore inhabit not just a hole in matter, but a place where the future trajectory of cosmic emptiness is already unusually advanced. That thought changes the mood of the story. The void is no longer only a problem for measurement or a challenge to the cosmological principle. It becomes a preview. In the larger sense, the future of the universe appears to belong to empty space. Dark energy continues to dilute matter's influence, widen the gaps between structures, and isolate gravitationally bound islands from one another. A void shows this future in concentrated form. It is where that long trend is easiest to read. The KBC void, if real in the stronger sense, may therefore matter not only because it skews the local Hubble constant, but because it gives the Milky Way an unusually clear view of the universe's eventual preference for hollowness. The observer lives where gravity is weak, where expansion gains ground, and where the dominant component of the cosmos can be studied through what has gone missing. The strangest part is that the cleanest clues do not come from where the universe is brightest. They come from where it has almost emptied itself out, and if those clues continue to sharpen, the local hollow may turn out to be more than an anomaly. It may be the nearest place where the hidden engine of the late universe can be seen at work, not through what it creates, but through what it steadily leaves behind. A void is not only a record of what the universe has been, it is also a sketch of what the universe is becoming. The same processes that make these underdense regions unsettling in the present make them even more important in the far future. Matter clumps under gravity, but gravity has limits. It can bind galaxies into groups, groups into clusters, and hold stars inside galactic disks and halos. It cannot hold the whole large-scale web together against the accelerating expansion of space. The great filaments and walls that now seem like permanent architecture are not permanent at all. They are temporary arrangements suspended within a universe increasingly governed by empty space. As dark energy continues to dominate, the underdense regions widen, the separations between rich structures grow, and the web begins, very slowly, to fray. In that long unfolding, voids are not side features. They are the direction of history. They are what the cosmos becomes when time is given enough room to work. This gives the KBC void a strange double meaning. In the present, it may be an anomaly large enough to distort the local reading of cosmic expansion. In the future, it may look less like an anomaly, and more like an early local preview of the universe's preferred condition. The hollows grow while the bright structures become ever more isolated. Galaxies that are not gravitationally bound to one another drift farther apart until their light takes longer to cross the widening gaps than the future universe allows. Horizons tighten. More distant structures recede beyond causal contact. Their light, stretched and weakened, fades into wavelengths too long and too cold to reveal the worlds that emitted it. The sky does not become instantly empty. It thins by degrees, as though the visible universe is being erased from the outside inward. What remains bound remains visible. What is not bound is slowly surrendered to expansion. For the Milky Way and Andromeda, this future begins locally with collision rather than isolation. Their approach continues, tides deepen, and in a few billion years the two galaxies merge into one larger remnant. The smaller members of the local group become part of that same bound environment or are scattered through it. From the standpoint of local gravity, this is not a dissolving but a consolidation. A new giant galaxy emerges from the union, holding onto its stars, dark matter, and remnants long after the wider universe has begun to vanish from practical view. This detail matters because it reveals the scale at which dark energy does and does not win. It does not pry apart what gravity has already firmly bound. It works on the larger gaps, the broader architecture, the space between groups, between clusters, between superclusters. It turns the universe into islands. The local group survives as one such island, but the sea around it keeps expanding. Inside a large void, that isolation arrives with special force. The Milky Way already inhabits a relatively sparse region compared with the richest nodes of the cosmic web. As the underdense environment expands more effectively than dense surroundings, the contrast deepens. The distant filaments and clusters beyond the local region grow harder to observe. Light from them takes longer to arrive and arrives increasingly impoverished. What is now a universe full of distant galaxies, surveys, background radiation, and measurable structure may one day become, to any observers who still exist, a much smaller visible reality. The cosmic microwave background itself continues to cool and redshift. Over immense time it becomes fainter and harder to detect. The evidence for the hot beginning of the universe, so central to modern cosmology, does not remain forever easy to find. In a dark enough future, it may become effectively invisible to any civilization limited to the instruments and horizon of its age. This leads to one of the most unsettling speculative consequences of the void. A civilization born deep in such a future, especially inside a sparse region already prone to observational bias, may not infer the true history of the universe at all. It may see only its bound local island, a merged galaxy and a few nearby companions, surrounded by apparent emptiness. Without access to distant recession, without a detectable microwave background, without a rich visible web of external structure, the most natural cosmology available to such observers may be a static, isolated universe. The larger expanding cosmos, the early hot plasma, the primordial fluctuations, the great web of filaments and voids, all may lie beyond reconstruction. The true shape of reality would still exist in principle, but the observational path back to it would have closed. A void, therefore, does not merely distort measurement in the present. In the far future, it may erase the evidence needed for accurate cosmology altogether. That thought folds back on the present with quiet force. If future observers can be trapped inside a misleading local sky, then perhaps present observers must take seriously the possibility that they too live under a softened version of that same condition. The KBC void becomes a warning written in advance. It suggests that cosmic understanding always depends on what remains visible from a particular environment at a particular epoch. Humanity may live at a fortunate moment, when ancient light is still detectable, distant galaxies still crowd the telescopes, and the structure of the web can still be mapped well beyond the local group. But fortune is not the same as neutrality. Even now, the local environment may already be skewing interpretation. The void shows that being early enough to see much of the universe does not guarantee being placed in a region that represents it well. Speculation about life inside voids sharpens the tension further without resolving it. Sparse environments are often imagined as hostile because they contain fewer galaxies, fewer stars, fewer metals, and therefore perhaps fewer worlds on which chemistry can become complicated enough for life. Yet the same sparse environments may also be quieter. Fewer close galactic encounters, fewer dense cluster cores, fewer catastrophic energetic events from nearby crowded regions may create long stretches of relative stability. A galaxy in an underdense region can evolve slowly. Its habitable worlds, if they exist, may endure under calmer skies. The balance between scarcity and stability remains uncertain. The universe offers no obvious answer, but if life can arise in such places, then the void becomes more than a structural feature. It becomes a cultural and observational condition. Civilizations separated by great hollows may develop radically different pictures of reality based not on intelligence or care, but on what the large-scale environment allows them to see. In that light, the KBC void almost ceases to be a simple astronomical object. It becomes a lens through which to ask how much any observer can truly know from within a particular cosmic habitat. The Milky Way may be located in a region whose lowered matter density affects galaxy counts, bulk flows, and the local expansion rate. Future inhabitants of similar or even emptier regions may find the broader universe almost irretrievable. Somewhere in between lies the present condition, rich in evidence but not free from bias. The void does not merely separate galaxies, it separates possible understandings of the cosmos. It can make one civilization infer acceleration too strongly, another not at all, and still another never suspect a larger universe beyond its own island of stars. The long fate of the cosmic web makes this even more poignant. With enough time, the web itself is not the permanent truth of the universe, but a transitional phase. Filaments thin, external clusters disappear beyond the horizon, star formation wanes as gas is consumed or heated or lost, and the surviving islands grow older, redder, dimmer. Black holes persist longest, but even they are not eternal if the broad expectations of quantum evaporation hold. The final stages belong to a universe increasingly dominated by dilute particles, fading radiation, and distances so large that causality itself becomes a local privilege rather than a cosmic common ground. In that far future, voids do not stand out against structure. They are structure. They are the overwhelming condition into which everything not securely bound is gradually absorbed. And that is the deepest reason the local hollow matters. It may not only help explain a mismatch in present measurements, it may reveal, in advance and in miniature, the direction of the whole cosmos. The observer may live in a place where matter is already thin, where outward flows already complicate the clean reading of expansion, where the assumptions of typicality already tremble, and where the future reign of empty space is easier to glimpse than elsewhere. The KBC void then becomes more than a local irregularity. It becomes a frontier between two ways of imagining the universe, one in which the cosmos is fairly sampled from almost anywhere, and another in which location quietly governs what can be known. Nothing in this story closes cleanly. The void may prove shallower than feared, or more decisive than expected. It may explain part of the Hubble tension or only deepen it. It may be a rare accident or a sign that large-scale structure forms more violently than standard theory prefers. But if the Milky Way truly drifts inside a hollow of this scale, then the universe is not only stranger than it once appeared. It is more local, more dependent on vantage, more willing to let emptiness shape meaning, and beyond the bright lanes of the web, beyond the measurements and the debates, the hollows keep widening, as though the cosmos is slowly teaching that what is missing may one day become the main thing there is.